Hi, this is Professor Fernandez working on class notes A in lesson 11. So in this example, I want to talk a little bit about linear independence, dimension, basis, span, all those concepts that we've just introduced earlier in the lesson. So let's start easy in terms of just the complexity of the spaces we're going to look at and look at the space R2. So we're representing here R2, this is the Cartesian plane, as a set of vectors. So specifically vectors of two components where each component is a real number. Okay, and what's the first thing we're going to show? We are going to show that the two vectors here, excuse me, form a basis for R2. And then the question is, what is the dimension based on this fact? All right, so we want to show that these two vectors form a basis. Let's scroll up a little bit to remind ourselves of what that means. So what does it mean for a set of vectors to be a basis? Well, so here is the definition. So let me clear things up here so we can focus a little easier. So a set of vectors is called a basis if it spans and is linearly independent. Okay, so there are two things to check: linear independence and span. And what is linear independence? I want to make sure that no vector can be written as a linear combination of the other ones. And I check that by forming a linear combination right here, setting it equal to the zero vector, and showing that the only solution is all zeros for the c's. Because, why does that show linear independence? Because if at least one of the c's is non-zero, let's say it's c1, let's say it's like 2x1 plus dot 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 equals 0, then I can solve for x1 by dividing by 2, and I can say x1 equals a bunch of stuff divided by 2. So I, in fact, have been able to express x1 as some linear combination of all the other x's, right? And that is not what we want to be able to do for linear independence. Okay, so that's linear independence, so we'll check that in a minute. And then span, what is span? So span is we want to be able to express every element of the vector space as a linear combination of the vectors we're claiming span. So can I take any element of the space and decompose it as a linear combination of these n vectors that I'm claiming span? Okay, if I can do that with these n vectors, they are Li and they span, then they are a basis. And then what is the dimension? I just count the number of basis elements. If there are, 5 vectors that span and are linearly independent, the dimension is 5. Okay, as an example. All right, so let's do that down. Go down here and go back to these two vectors and show that they are a basis. So first thing I'm going to do, so this is part A, first thing I'm going to do is do the linear independence. So I want to set up C1v1 plus C2v2, set it equal to the 0 vector, and I want to figure out, does this imply that all the C's are 0? So let me, on the left-hand side, start putting in what I know about the vectors. Okay, and I am going to try here to solve for C1 and C2. Okay, so I multiply in the C1 in, and I get C1, C1. I multiply in the C2, I get C2 minus C2. And then I combine this into one vector, C1 plus C2, C1 minus C2. Excuse me. And out pop a system of linear equations, right? What a surprise. Doing linear algebra and you get a system. At some point you have to solve a system of linear equations. Okay, so many methods we've talked about for doing this at this point in the course. I will always use the simplest method to save time and to be efficient. In this case, the simplest method is to just add these two equations. So if I do that, I get 2c1 equals 0, which gives us c1 equals 0. And then any one of these two equations, both of them, right, show me that c2 equals 0. So I have indeed set up my linear independence condition, and I have concluded through the use of our methods for solving linear systems that C1 and C2 are 0. So check, right? So these two vectors are linearly independent. Now I want to do the spanning part. So for the spanning part, I have too many numbers to keep track of here. So for 2, so span. So I'm going to let x be a vector in R2. Okay, So X, I'm going to say, has the form AB. Question, can X be written as C1V1 plus C2V2? Okay, so that is the question for span, right? Can I decompose a general element of the space as a linear combination of V1 and V2? So what does that mean? So here's X equals C1V1 plus C2V2. And this right-hand side we had already reduced to this, combined to this vector. So if I eliminate what's, the clutter here, so I can have a little bit more space and just clarity of mind, then what I need to do for span is I need to check whether this new system of equations down here is one that I can in fact find C1 and C2 values for. Okay, so what is the new system that I'm left trying to solve? Well, if I compare the first component of the right-hand side with the first component of the left-hand side, I get C1 plus C2 is A. The second one is C1 minus C2 is B. Excuse me. Again, I want to solve for C1 and C2, so I will take the simpler approach, just add the two equations. I get 2C1 equals A plus B. So that tells me that C1 is A plus B over 2. Great. So now I'm going to take that C1 and substitute it into maybe this first one. So if I put C1 in there, I get A plus B over 2 plus C2 equals A. So that tells me that C2 is A minus A plus B over 2. So common denominator gives me 2A minus A plus B. So I get 2A minus A, that's A, and then minus B over 2. Okay. So to recap, this is my C1, this is my C2, and in fact, if I put those C1 and C2 values in where they belong over here, then I have just shown that any element in R2 can be written as a linear combination of these two vectors. So that's exactly what it means for those two vectors to span. So check. So we've just shown that the two vectors span. Great, so they are linearly independent and they span. So by our definition, that means that they form a basis. So now we know that the vectors form a basis. And then to find the dimensions of these vectors, what do I do? Well, remember the dimension, of the vector space. What do? I go back to the definition. So what is the dimension? A couple of minutes ago or so, we talked about it. The dimension of R2 is the number of elements in the basis. 2 is 2. Okay, I'm sure you already knew that, right? This is the plane two-dimensional space, but this is one of the really cool things about this particular set of topics. We now have a definition for the dimension of a space. It has to be a vector space. That's the definition we're studying, but you can actually calculate the dimension of a vector space. So that's pretty cool. You don't have to, use your intuition anymore. Although, obviously that's still a good thing to do. Okay, so in part B, I want to do something a little differently. So in general, when you meet a vector space, right, you want to try to very quickly find a basis for that vector space because it simplifies working with the vector space and helps you understand the vector space and its structure better. In part A, I gave you two vectors and then asked you to show that they form a basis. So, you didn't have to search for a basis. I just gave them to you, and the idea was to show that they're a basis. But that's not going to be true in general. If you, encounter a vector space in the wild, you open your door one day to go outside for a walk, and there's a vector space, right? How do you know? How do you find a basis for that vector space? So that's the point of part B here. So I say find another basis for R2, so another basis, by decomposing a general element of the space into simpler elements of the space. Okay, and then verify the dimension you get is the same as you got from A. So this little part here, I'm gonna really emphasize. This is a really good way to start off getting some candidates for the basis for a vector space. decomposing a general element of the space into simpler elements of the space. Okay? So let's start doing that so I can show you what that looks like. So what do I mean? So again, let's take a general element of the space, AB, right, in R2. So I want to try to start with a vector AB and decompose it into simpler vectors in R2. So, it might take a while for you to think about how to do this, and this is the first example in this lesson. So it's intended to help you develop this skill. But if you think about this for a while, what is this vector? It says go A units in the x direction and then go B units in the y direction. So you might decompose it by saying, okay, go A units in the x direction, don't move in the y direction, and then go B units in the y direction, don't move in the x direction, right? That's a nice decomposition. And then from here, you might think to say, oh, okay, so A units in the x direction is actually A times 1 unit in the x direction, right? And B units in the y direction is B times 1 unit in the y direction. So then notice what I've done. I have decomposed a general element in the space into what is now a linear combination of two specific vectors. So actually, this shows that 1, 0 and 0, 1 span R2, right? Through this decomposition argument, I've just shown that these two new vectors actually span the space. So I'm kind of like halfway done to a basis. And that's why I mentioned earlier, this is a really useful way to look for a basis, because you will, in this decomposition process, discover very transparent candidates for the basis, right? So I'm going to call these two vectors E1 and E2. This is sort of the standard notation for these vectors. And the number here refers to where the 1 is in the vector. So E1, the 1 is in the first component. E2, the 1 is in the second component. After this, I'll scroll down and show you what this looks like for Rn, n-dimensional Euclidean space. Okay, so this shows that they span. Now let's show that they're linearly independent. So I'm going to go back and do the same check. Is it true that when I form an arbitrary linear combination of E1 and E2, that C1 and C2 are both 0? Okay. Well, on the left-hand side, this is C1, 1, 0 plus C2, 0, 1. That's kind of like going back up here, except A is C1 and B is C2. So I can just fast forward to over here and simplify down here this to C1, C2. Okay, so I am trying to show that if C1, C2 equals 0, 0, that implies that C1 equals C2 equals 0. And the answer is yes, right? So C1 setting the first components equal is 0, and then C2 setting the second components equal is 0. Great, so I now know that they are linearly independent and they span, right? So I have found another basis for R2. So let me remove all the clutter so I can write down this basis, and then we can talk about its dimension. So I found another basis for R2, very cool. And this basis is a little simpler than the first basis that we talked about. That's also very nice. So E1 equals 1, 0, E2 equals 0, 1 is another basis for R2. Dimension count. So dimension of the space is the number of elements in the basis. So this one has 2 elements. So once again, dimension of R2 is 2, which is, what we got in part A and certainly what we would expect. Okay, so last thing that I was going to mention is what I said about the more general versions of these vectors E1 and E2 for R3, R4. So in a future video, I'm going to scroll down a little bit here. Let's see, I'm going to scroll down a little bit right here. So I say a little further down the notes. In general, the vectors E1 through En where EI, as we said, means that you have a 1 in the ith row, form an n-dimensional basis for, or I should have said form a basis for Rn, and imply dimension of Rn equals n. Okay, not that what I said is wrong. It's just not going along with the way I've been expressing these concepts in the earlier example. Okay, so this is what some people call the canonical basis of Rn, or the standard basis of Rn. And the last thing I'll mention, if I scroll up a little bit here to what we just showed, is that when you step back from this example, you realize that we have seen that a vector space, in this case R2, has not only this basis, but also another basis. Okay, so again, that's an illustration, if I scroll up here, of this first fact. Bases of vector spaces are in general not unique. All right, so that's the end of this video.